Hi everybody. We're going to start our reaction section of this unit by reactions to make esters. So look at all these fruits. You can see that there's an ester on each one of them. And you should be able to name them all. So let's just look at the raspberry one. It's got here's the R part, and it's got 1, 2, 3 carbons with a methyl on carbon 2. So it's 2-methyl propyl. One word, that's one word, 2-methyl propyl is the R part, and then the O8 part has 1 carbon, methanoate. And O8. All right, so after this PowerPoint, you should be able to know the chemicals it would take to make that. Okay, and you can name all of these, and we can look at those. Okay, so 2 main ways: Fischer esterification, woohoo, which we already learned in the alcohol chapter. A subcategory of that is lactone formation, which is a Fischer esterification, but we get to learn a new term and a new type of molecule, sort of. And then alcoholysis of an acid chloride. So here are the 2 main reactions that you're going to be putting on your summary sheet, but really it's 3 so that you know what a lactone is. Okay, so a general Fischer esterification equation is, it's general or generic because it's R. You have to use a carboxylic acid and an alcohol with an acid catalyst to form an ester and water. One main thing to note here is that, I'm going to change to red, the R part of the alcohol ends up as the R part of the ester, okay? So R prime of the alcohol becomes your ester R, if you will, ester R. That's the main thing that really happens. Now, if we look at the mechanism, which we will, it's really the OR of the alcohol ends up where the OH used to be, but you couldn't just remember that the carbons from the alcohol end up being the R of the ester. Okay, so there's a video that you're going to watch. You can click on in a different on Canvas to watch the explanation of the mechanism, but I also have it on the slide. So here's what happens. Here's your acid catalyst, right? And then your acid catalyst catalyzes or protonates the alcohol, and or it just protonates the carboxylic acid. So the hydrogen of the carboxyl oxygen will grab a hydrogen. The oxygen will grab a hydrogen, protonate it, and so now the alcohol, this carbon of the carboxylic acid will now be a little more positively charged because of that protonation. Okay, and so then the alcohol will attach to the central carbon of the C double bond O, and then there's more alcohol that will pull off the hydrogen. Okay, and so now we have the OR there, but there's still more proton transfer going on. And then the double bond can reform and kick out of water. So kicking off of water, because water is a good leaving group, is part of what drives this reaction. And then deprotonating gives you your ester. Okay, and you'll get your acid catalyst back when you deprotonate. So the alcohol R's end up as the R of the ester. Okay. Another way to look at it is this way. So here's the acid protonating again. Alcohol comes and attacks that carbon, kicks up the pi electrons from the double bond. There's some proton transfer going on, and then eventually it gets deprotonated, and then you have the carbons that were part of your alcohol are now the R of the ester. Okay, so how is that different than internal Fischer esterification? It's not. The difference is in internal Fischer esterification, you have a carboxylic acid. So here's the carboxylic acid part of the molecule. And that same molecule has an ROH. A what? An alcohol. So we have an alcohol and a carboxylic acid in the same molecule. And then with protonation, then this can all happen within the same molecule. So here's the 1, 2, 3, 4, 5 carbons. And so we have the 1, 2, 3, 4, 5 carbons, and then the O of the alcohol, and then the C double bond O from the carboxylic acid. All right, so now we have an ester. Now this isn't any old ester. It's called a lactone. And the next slide will show you what lactones are. But as you can see, we don't lose or gain any carbons, we just ring them up, okay? So lactone is an ester in a ring. You lose a water molecule along the way. And this one, here, I'll make this one red. That's this one. So we've got 1, 2, 3, 4, 1, 2, 3, 4. And so you make a ring ester. So it's still a Fischer esterification with a carboxylic acid and an alcohol. And you make a ring ester, you make your ester in water, but it's all in the same molecule. Okay, so it's a lactone. Here's what a lactone is. It's a cyclic or a ring ester. All right, so we have a COO. Are you a lactone? Yes, I'm going around that carbon. So the R connects back to the carbon of the C double bond O. Right? So this is a very stressed one because that's hard to do. This one is a little better, and then they get as they get bigger, they get more stable. Okay, so where would you find these lactones? Well, here's the one in the peaches. All right, you find them in vitamin C, ascorbic acid. So ascorbic acid has two forms, and so one is a lactone form. All right, and you have COOR, ascorbic acid. Yeah. Okay, so this is a lactone form. All right, here's a couple other lactones. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it's really close, but they're a little different. And sometimes you'll see these Greek letters here, like there's a delta non-lactone, there's a gamma non-lactone. Okay, and so if we look here, remember this was carbonyl carbon, alpha, beta, gamma, carbonyl carbon, alpha, beta, gamma, delta. Okay, so you won't have to know that, but that's where that's coming from. All right, so here's some lactones. So now we know how to use Fischer esterification to make a lactone. So here's another 1, 2, 3, 4, 5 carbons here, alpha, beta, gamma, delta. All right, and so when that rings up, you get a delta lactone. Right? And then this is a gamma lactone and a beta lactone. Right? So that's where the Greek letters are coming from. That's what they mean. So alpha is first off the carbonyl carbon, beta, gamma, delta. Right, there you go, lactones, that's how you can make them. It's really a Fischer esterification with a carboxylic acid and an alcohol, and then it rings up to make a lactone. Okay, the last reaction in this PowerPoint is to make an ester is alcoholysis of an acid or acyl chloride. Right, so it's called an acid chloride because it's C double bond O, and this used to be an OH, but if it has a Cl there, it's called an acyl chloride. Sometimes that's called an acid chloride. All right, and so here's an alcohol. So the two reactants you need, and this is just a pyridine can be used, and tetraethylamine can be used, and you get a little slight variation on the HCl, but we're gonna ignore this part. All right, this we'll put optional. All right, and this part we'll put optional. But here's what I want you to notice. You take a carbonyl carbon with a chlorine on the one side of it, and then either an H or some other carbons over here. You add it to an alcohol. So you don't have to put this above the arrow. You can put it next to it, like we did in this one. And then the R from the alcohol ends up being the R's of the ester. Okay, so the chlorine gets kicked off, and the OR from the alcohol replaces the chlorine. All right. So this alcohol is OR, and the R is a phenyl group. Goodbye chlorine. There's your chlorine. Hey, we could even make that chlorine green because that's the chlorine that came off the acid chloride, right? And then the OR came from the alcohol, right? So those are the types of reactions. What we're making here are esters. And so let's see if we can do it. So you have propanoic acid. Prop means 3. 1, 2, 3. It's an acid, so it's on the end of the molecule. All right. Methanol. COH. Remember, this is CH3. All right. Acid plus alcohol. This is a Fischer esterification. So what happens is that the OH of the acid is replaced by the OR of the alcohol. So we still have our 3 carbons here. And now we have an O and then a C. All right, and that came from the methanol. Methanol All right, and then that came from the methanol. And so when that happens, water gets kicked off. And so we should be able to name that ester. So it's methyl for the R part, propanoate. Propanoate. All right, and water. So we're naming both products. Okay. 7, hydroxyheptanoic acid. What? All right, so hepta means 7. 1, 2, 3, 4, 5, 6, 7. All right, and so it's heptanoic acid. And then on carbon 7, 1, 2, 3, 4, 5, 6, 7, we have an OH. All right, sweet. This is with an acid catalyst. This has a carboxylic acid and an alcohol in it, so it's going to make a lactone. All right. So we're going to have our C double bond O. Now, this is hard to draw in a ring, so I'm going to just draw the carbons, and I need 7 of them. 1, 2, 3, 4, 5, 6, 7. And then the O, all right, plus water. All right, so it's really an 8-sided ring, 8-cornered ring, all right, but one of those is the O. All right, and then we have this thing, and this you have to recognize as an acid chloride or an acyl chloride. And then methanol is 1 carbon. Okay, so the OR part of the methanol is going to kick out the chlorine, so we're still going to get our benzene ring. Oh, not bad. All right, we still have this carbon here, and then that carbon of the C double bond O, 1, 2, 1, 2. All right, and then we got the OC from the methanol. Right. Now, when that happened, chlorine got kicked off, and the H from the alcohol got kicked off. Okay, so yes, you have to know the byproducts for these. For Fischer esterifications, it's water, and for alcoholysis of an acid chloride, it's HCl. All right, so that's it. That's the reactions. Hope you liked it, and